Next we have Brian Behlendorf. Brian is a computer scientist at Lawrence Livermore National Laboratory. He's been working on Linux coding projects for 9 years. His latest project is a native port of ZFS to Linux. Take it away.
Hi. Yeah, I've been working on a port of ZFS on Linux for Lustre. So I didn't want to spend too much time in the past, but I do think it's worth going back a couple of years to figure out why this project's been started, because it's been underway for a while. You've probably noticed that every couple of years there's a ZFS talk that gets presented at LUG. And that's because there's actually been a lot of activity for the last couple of years. So in 2007, Livermore started having concerns about long-term LDiskFS scalability and performance, particularly for our next class of large file systems we wanted to deploy. Dave Dillo did a good job of summarizing the problems we have with LDiskFS. I think they're well known to pretty much everybody in this room. Offline FSCKs, they take a long time, file system limits. We see random I/O issues with LDiskFS. I'll come back to more of that, how ZFS helps us there, and the data integrity issues. So we identified the need for an alternate back-end file system for large Lustre file systems. LDiskFS may be perfectly suitable going forward for quite a while for the smaller file systems. I mean, it's a workhorse, it's tried and true. But for the largest Lustre file systems, it's clear there's going to need to be something else. We looked around at the time and identified ZFS as probably the technically best solution out there. It addresses all the known limitations of LDiskFS that we were most concerned about. And importantly, even at the time when we looked at it, it was a proven production quality implementation. That takes a long time to get there. So starting with a known code base is good, especially something that's has a proven track record. At the time we started this, there were licensing concerns. I'll talk more about that later, but they were believed to be addressable, and I think we still think they're addressable. But the problem is it needed to be ported to Linux. It only existed on Solaris. So Sun ZFS at the time, actually, started a ZFS Lustre port in user space. In 2008, Livermore started our port to the kernel. This was basically intended to determine the viability of a kernel port, if this was something that was going to be feasible in Linux. The prototype turned out pretty well. We had no unsurmountable technical issues really uncovered, things that could be addressed, and initial performance was actually pretty encouraging. So we decided to try and convince Sun that this is the way we should go in the kernel. They agreed eventually, and I joined their development team, and Lustre OSD development continued. Andreas and Dave also mentioned with the Lustre OSD stuff, so since we're running short on time, I don't know if I want to delve too much into that, but it's basically just restructuring Lustre to support multiple backends, right? A simple task. It's been a couple of years now, but we'll get there. The licensing concerns were still unresolved, and work pretty much continued. In 2009, Livermore was mainly focusing on the ZFS component of this in the port, leaving the Lustre refactoring to Sun Oracle at the time. Was focusing on making our port more production quality. It needed to be stable first because we're going to be running this in production. Stability first. Let's make sure we can get there. So we built a quarter scale system, and that was actually a great aid in actually running down a lot of the stability bugs. So in 2009, we actually had a pretty stable implementation to work from. Oracle acquired Sun in 2009, a lot of churn, but really not a lot of change from our perspective on the Lustre OSD development. Development continued. They're working on issues like zero copy, the grant code, large D nodes is a ZFS feature that needed to be worked on, quotas, integrating the Lustre utilities. Once again, the licensing issues were still unresolved, but work continued. 2010 comes around. Livermore's working now on basically integrating ZFS cleanly with Linux. So that means getting the utilities in place, getting the hooks in UDEV, added something called Z-Events, which is kind of analogous to the Solaris FMA infrastructure, if you're familiar with that. And we actually went through an exercise to verify that disk failures were handled properly, and you could do horrible things to the system, and it did what it was supposed to. Once again, that goes back to just being stable and for production implementation. We built out a full-scale ZFS Lustre file system, and it basically held together and worked. So it was actually really encouraging. On the Oracle side of things, Oracle announced that ZFS Lustre would only be available on Solaris, and that was a bit of a bummer. But behind the scenes, actually, development continued on Linux for the Lustre OSD stuff, with the intention of it being moved to Solaris eventually. That's what Oracle canceled feature development on Lustre. That finally delayed progress a little bit. So licensing concerns still not resolved, but we're continuing at Livermore. We were still committed to moving forward on this plan. So in 2011, we finally added the POSIX layer to the ZFS on Linux. That was nice. That was something people were waiting for a long time. It's not really required for the Lustre port, but it's helpful to have, not just from a testing standpoint, but just to get broader adoption and use of the code. So we actually invested the time to get that done. There's a beta available of it now if you want to download it. We also made the Lustre OSD development branch publicly available. So now all the source code is available. You can get it, download it, try it. I suggest you use RHEL 6 because that's what we're developing on. WhamCloud also just recently signed up to help us take on this Lustre OSD development task and get it done. It's been worked on for years, and we'd like to see it completed. So Livermore contracted that work to be finished, the restructuring of the Lustre OSD, or at least partially fund the restructuring of the OSD. Most of the original Lustre OSD developers are at WhamCloud, at least a large fraction of them, so it's the same group working on it. Licensing, still not resolved, but work continues. We're planning in late 2011 for a 50 petabyte file system still. So it's going to be, the target is a ½ terabyte a second with a stretch goal of 1 terabyte a second. So that's really what's been driving this work for the last couple of years is the Sequoia system's been looming on our horizon, and we're a little concerned about deploying something LDiskFS based for a file system that large. So I can probably skip this slide. I mean, if you're not familiar with ZFS, it's a file system developed by Sun, combined file system, RAID manager. Some of the nice features are copy on write. It has a great built-in data integrity. That's been rule 1 for ZFS. Online scrubbing and resilvering, those are their terms for basically an online file system check and a disk rebuild, and no file system limits really. So as I mentioned earlier, our reasons for doing this were LDiskFS was getting a little long in the tooth and needed to be replaced. Some of our big issues with LDiskFS were performance related. It turns out that in our large systems, write performance isn't really bound by the disk bandwidth. It's constrained by disk IOPS. So if you've got enough Lustre threads generating a workload on Lustre on an LDiskFS file system, they basically look like a random workload of 1 megabyte IOs for a good workload. So 1 megabyte times your IOPS rate, that's what you're going to get out of an LDiskFS file system. You may see better rates if you actually have a few number of objects active on an OST, but if you've got 500 or 1,000 objects being concurrently accessed, it pretty much degenerates into random from our experience. Size limits were a problem. FSEK times were getting worse, and they're only going to continue to get worse as file systems get bigger. Sure, you can make the file systems bigger within limits, but you just make the file system check times longer. There's things you can do. Really clever ideas actually have been floated to mitigate this issue, but it's still offline, and that's not good. Once again, our requirements for the year, but the big thing here is that we need to do it at a price we can afford. And using ZFS actually lets us eliminate some expensive components from the system because it's got its own built-in RAID system, so you can get rid of those expensive storage controllers. Just plug it directly into the disk. So ZFS also supports copy on write, which is one of the nice features that actually helps us a ton for this random I/O problem. You can take the random I/O, and because it's copy on write, it not only closes the RAID write hole that I think people are pretty well familiar with, but it also has a side effect of serializing all your I/O potentially. So you can take a completely random workload and make it serial, which is great for disks, because especially cheap disks. No volume size limit. ZFS has a file system check. It's not an offline file system check, but I personally view the ZFS scrubbing as an online data check. So I mentioned licensing earlier. I only want to briefly touch on this, but it's something that always comes up, so I feel it would be negligent not to at least briefly talk about it. So there is a licensing issue with ZFS, which I think most people are aware of who've looked at it. Lustre, the Linux kernel, and a shim layer I wrote are all GPL code, and ZFS was released under the CDDL license, which is an open source license. It's actually not in my view, a particularly bad open source license. All the code's available, you can download it, you do what you want with it, but the GPL and the CDL are incompatible. So the ZFS code can't be directly integrated to the Linux kernel tree, for example. So I'm not a lawyer, but we did talk to our lawyers. And they agree that what we're doing is fine. What we're doing is distributing source code for ZFS at the moment. So we've taken CDDL, which is an open source license. It also, interestingly enough, provides explicit patent licenses for everything covered in the CDDL code. So I know there's a lot of confusion about using ZFS safely, but you actually are granted patent licenses. So all the changes we've made to ZFS have been contributed back to ZFS as CDDL license code to a standalone ZFS repo, which is completely separate from all the GPL code. So all we're doing is taking open source code for ZFS, posting it back online as open source code under the original licenses. So we're sure that there's nothing wrong with that. You're welcome to download the code, combine it on your site. We've tried to make that process easy. Binaries are admittedly a little bit of a gray area. I don't want to dwell on them too much either. But the Linux kernel does allow third-party modules that are, pre-built binaries. NVIDIA, ATI, all have kernel drivers that are not just proprietary, but they're all closed source, and you can't see anything. They're allowed to load into the kernel. Linus's view in general on kernel modules has been that the interface is an LGPL interface. It's a library interface, which means you don't need to have a GPL license module. However, in the kernel, certain symbols are flagged as GPL only. We go through careful effort not to use any symbol that's explicitly marked GPL only. And also the issue people tend to have with binaries is you are building against a Linux header, so you're actually including Linux sources in your pre-built binaries. That's believed not to be a problem. I've got two quotes just to kind of back up what I'm putting out here, so you don't just take my word for it. But a lot of this hinges on ZFS not being a derived work of Linux. Back in the day, Linus had this to say about the AFS file system when it had a similar issue. I can just let you read it quick while it's up there. But so I think that was pretty analogous to where we are today. And of all people, on the included header issue, Richard Stallman, who view at the FSF, was basically that including headers isn't enough to make a drive to work. So those are two opinions of two people, right? And it's in the gray area, but we think that's okay. Sources are clearly fine. Binaries, probably fine too. So anyway, how does this all work? So the port of ZFS basically sits on top of a shim layer that we wrote at Livermore called the SPL. It's called the Solaris porting layer. The idea here was ZFS was a mature and stable file system already at this point, and we wanted to make as minimal changes to it as possible because fewer changes we made to it, less likely we were to destabilize it, introduce subtle bugs, anything like that. So if we could preserve all the interfaces and as much of the ZFS code as possible in the port, that was going to be good for stability long term. They had tons of testing hours and effort in fixing all those bugs, so we don't want to introduce new ones. So what the SPL layer does actually is it provides Solaris-like APIs, kernel APIs, for ZFS to consume in the kernel. ZFS and Lustre Components. So ZFS fundamentally is structured into 3 layers. You may have seen a very similar diagram to this on the Sun website. The bottommost layer is the pool storage layer in ZFS. It basically manages configuration, the ARC cache, how VDEVs are controlled. Those are basically the lowest level of device management in ZFS. On top of that sits the real heart of ZFS, which is the bit that we're most interested in for Lustre, called the transactional object layer. The real core of this is the DMU, which provides a very nice, clean transactional object interface for whatever end interface to consume. So on Solaris, the two things that basically use the DMU are the POSIX layer, known as the ZPL, it's your mountable file system. It's just a nice layer that sits on top of the DMU, written against that API. And they have something called a ZVOL, which is a virtual block device, basically. The idea here is Lustre is going to tie into exactly this same level and just sit as its same component, tying into the DMU and a couple other services at that level. So Livermore's basically, like I said before, focusing on the ZFS portion of this. We've basically ported the whole stack at this point. and it's all available in our sources, which are online for Linux. CFS, then Sun, then Oracle, now WAM Cloud, have been working on the big restructuring project of restructuring Lustre to use multiple backends, and in particular to tie into ZFS. So this is their restructured stack. The idea here is that ZFS would have a ZFS OSD, which integrates with ZFS, and you could also redraw this diagram with a LDiskFS OSD that plugs into an LDiskFS file system, or a ButterFS OSD at some point. I believe we're going to have a nice talk about that later. I'm actually looking forward to that. So how is Livermore going to use this code? We've built a prototype file system called Zeno at the moment. It's what we call a SSU, storage scalable unit at Livermore. It's kind of our fundamental building block for how we build clusters. We'll buy multiples of this basically to build the file system. So this is our original Zeno OST. This was our first design for how we might build a scalable unit using ZFS on Linux with commodity components. The block diagram basically shows 10 60-bay enclosures attached with SAS connections to 8 hosts. Each host has 10 SAS links in it, and they're attached through a QDR IB switch. The nodes act as failover partners for each other. Each SSU had about 900 terabytes of capacity, should hardware peak at about 25 gigabytes a second, and the disk was arranged on each host in 70 drives per host in 8+2 RAID groups. Although if you look at this data a little bit, if you can see the bandwidth numbers in the speeds and feeds table there, we're actually being limited by the QDR IB bandwidth on this system, and we've got way more disk and SAS bandwidth than we need for this system. So we thought maybe we could do a little better. So we went back, and one of the nice things about ZFS is that we've got a lot of flexibility over our components and how things can be put together. So we said, okay, we'll try a different design here. We think we can do better. So this is a restructured Zeno, which has 960 terabytes of storage. It peaks at 38 gigabytes a second about, and has fewer drives per node. So what we basically did here is increase the node count by adding SAS switches. Each SAS switch is attached to all 10 drawers. We have 4 switches, and then each node is attached to 2 switches. So the idea is to use a DM multipath so that we don't have any single point of failure. We can lose a SAS switch, won't be any problem. The nodes are still set up in a failover configuration, so if you lose a single server, you can do Lustre failover to the other. But it's easier if you don't have any failures, so we try to handle some of the failures for the unlikely event of a SAS switch lower too. So this is our next thing we're going to build up and verify that this works, because this improves our performance with the exact same amount of disk, right? And it's actually a little cheaper than the first design because we eliminated a large number of SAS cards from the host. Oops, let's get that. So where are we at today with performance? So there's a benchmark with ZFS called ZPIOS, which we've been using to get our performance numbers. It's designed to simulate a Lustre workload, so it creates a lot of kernel threads, and they all issue, with our parameters, random 1 megabyte IOs from a lot of threads to a lot of different objects in the kernel. So it's designed to simulate Lustre's service queues. What we found actually is the benchmark turns in numbers that are really comparable to what we see when we run Lustre on top of ZFS on our test systems. They actually map very, very well. So this graph shows on the left, I don't know if you can read it, I guess not, megabytes per second, and then on the x-axis there's an increasing number of disks per VDEV. So on the right side, I guess, is actually where you want to look, and each line is a different type of RAID configuration. So the green line basically shows where we're at today for the original Zeno configuration for a RAID Z2 configuration of 70 drives. And that's, each node turns in about 1.2 gigabytes a second. We think there's some low-hanging fruit to be had here that can be improved. So we expect this number to go up. And if we could get it to saturate a QDR pipe, we'd be very happy. And we think that's probably possible. On the read side, things are actually quite a bit better. Read performance actually scales pretty well, linearly up to, again, 70 drives. And the numbers are much better with RAID Z2 topping at about 2,500 megabytes a second, which should be enough to saturate the QDR pipe. Unfortunately, for some reason that we haven't put our finger on yet, we don't see that when we actually run Lustre on top of it. We only get that with the benchmark. So there's either a flaw in the benchmark or some work on Lustre that needs to be done. But this is actually real data movement. We actually do see ZFS move this amount of data through the system. So that's encouraging. It's just a matter of identifying why we don't see that through Lustre as well. These tests were done with prefetching disabled. That's one of the things that needs to be looked into. For some reason, it goes faster with prefetching disabled than enabled. That needs a little looking at. So that's my talk. If you want more information about what we're up to at Livermore, there's a website, zfsonlinux.org. We've set up 3 mailing lists, and there's actually a pretty good community forming around this now that there's a POSIX layer available. There's also some links to documentation if you want to download all the ZFS, SPL, and Lustre sources and build them for yourself. Thanks.
It's noon, but I want to at least give an opportunity for a question or two.
Or catch me at lunch.
All right. Let's hit up John Carrier here. Thanks for meeting me.
What's happening with ZFS at Oracle now that they've taken control of it?
I have no particular insight into what's going on internally at Oracle, but I do know that they've made a new release for Solaris 11 Express. I guess they've moved the code base forward. They have closed the code base, so we don't no longer get any updates from them. There's some hope that that will be available at some point, that they'll choose with Solaris 11 to release the code, but that's up to Oracle.
You said your single node performance with Lustre, was that a parallel workload or a sequential workload, and what was that you were getting for numbers?
That was an IOR workload run from a large cluster. We ran the test once. On writes, the numbers are basically the same. We see a little over a gigabyte a second for writes. They agree very closely with the ZPIOS numbers. Reads, I forget exactly what the number was, but it wasn't great. It was on the order of, I think, I don't even remember, but it was some fraction of this. Do you guys remember offhand? Anybody? I forget what reads were, but they need some work.
Okay, one more? No? All right, be sure to talk to Brian at lunch. Thanks a whole lot, Brian.
Thank you.